Can you see the PDF file I've sent? There is a PDF on the announcement channel with some problems. Actually, there are also solutions, so for now, just try not to read them, because we'll discuss them later. Okay, there's a bit of silence here. Please tell something.
Second, SMS. No, participate. Do you need me to do anything or? Pretty good. No, participate.
Okay, start.
Mr. Stancanelli, I guess you can start the lecture now.
Okay,
Okay.
let's go. Okay, the first problem is not really about square root decomposition. I mean, you don't have an array, you don't have to answer queries. It's not like the standard square root decomposition problems, but you still need to use square root in some way. Okay, the problem asks to count the number of special pairs. A special means that A divided by B, floor, is equal to A mod B. And A must be between 1 and X, and B must be between 1 and Y.
So this is a problem and we have to find a solution for it?
Yeah. Okay, I'll let you think for a bit. I mean, just if you have an idea, just say it, then we'll discuss.
Aren't we going to do a for loop and then check if the condition is right? And you'll say yes or something like that?
For loop over what? Okay.
Yeah, over what? Alright. I don't really have an idea. I'm thinking that if we have a pair, let's say AB, and A and AB meet the condition too. I haven't proved this, but
wait a sec. I don't think so. Okay, I think if you multiply both by n, this remains the same, and this is multiplied by n. Let's try. So AB equals 3 to right, but if I multiply by 2, I guess this happens.
yes, I see, sir.
Okay, so let's actually try to find some partial solutions. Okay, of course, trying all A and B is very slow. But, okay, for example, if we try all values of A, can we find fast the number of valid B? Okay, I don't think so, because okay, let's see, or maybe yes. Okay, there's a trick you can use here. Do you know A divided by B floor reaches at most of square root of n values?
No, sir, I didn't know that.
Okay. By the way, actually it's useless in the problem, but okay, we'll discuss it anyway. It's very useful in other problems. Okay, if you have okay, let's consider the set of all A over B with A fixed A and B is any positive integer, and yeah, we want to count how many distinct values we reach. But okay, we can notice something. We have A over 1, A over 2, A divided by square root of B, square root of A. Okay, and all these values, okay, how many of them, how many values we have here? Square root of A.
They should be all the same value, right?
Okay, we are trying to count how many distinct values we have. And yeah, at the beginning, okay, we can try to plot it, and this is A divided by B, approximately. I'm not using floor. And the idea is this. Okay, this is the point square root of A. And then here, there are at most square root of A distinct values. And there are square root of A values in total. B equals 1, B equals 2, etc. Okay. 1, 2. Okay, and what happens here? Okay, here
They all become the same value.
yeah, we notice that the values are small. I mean, not really the same value because okay, let's try an example. You start with 9. Okay, let's divide 9 by 1, 2, 3, 4, 5, 6. Okay, 7, 8, 9. Okay, you see that here you have 3 values, and then all the values here are less than 3. So they are not really all the same, but still they are square root of A. So that's fine. Yeah, and there are a lot of equal values, of course, which in this case are equal to 1. Because yeah, B is less than or equal to square root of A. Okay, anyway, so in this particular problem we could just choose A, and then there are square root of A values of the floor, and try to do something here, but it's still too slow. The thing that we should try to do is, okay, let's just define this variable, and let's call it K. Okay, and then we can estimate how big can k be here. Okay, let's assume k is big in some sense. We'll calculate that later. Okay, of course k is a mod b, so we have b greater than or equal to k. Okay, but now let's also use this condition, and we have that a divided by b must be at least k. So we have a greater than or equal to b times k. Okay, but yeah, b is greater than or equal to k, so this is actually greater than or equal to k squared. Okay, so we have a till 10 to the 9th, which is greater than k squared, so k actually must be quite small. We have k less than or equal to square root of a, and that's it, which is square root of 10 to the 9th. Okay, so we should try to iterate over k instead of iterating over a or b or something. Okay, and now let's try to find all valid pairs a, b for fixed k, and they are okay. We have okay. Let's fix b, and now we have that. We have these two conditions. And actually, we know the exact value of a, assuming that we know the value of b. Because, okay, now we are just writing a in base b. And both the digits are k. So we have a equals kb plus k. Okay, so the problem just becomes count pairs kb plus k b with, okay, a must be at most x and b must be at most y. But yeah, now it's just calculations, well, not so interesting. We can rearrange stuff. This becomes k times b plus 1. So we have okay, we want to count the number of valid b. Okay. So we have something like b less than or equal to x minus k divided by k, and b less than or equal to y. Okay, and actually we also have this condition, let's not forget. What happened? B greater than or equal to k. Okay, so now it's just a for loop with one line, because here the valid values are all the ones in the range k minimum y x minus k over k. And this interval may be empty. Okay, if you see the code is really short, it's just doing this calculation. But okay, now I'd like to jump to actual square root problems. So I will not spend so much time on this problem. Okay, is there internet right now? Maybe not. Yeah, it's just this line. Okay, in this code, I is actually B. And okay, we have that A is okay, actually I think it cannot be equal. Okay, so we just remove the first B values. Okay, and we calculate the upper bound. Okay, yeah, by the way, you can redo the calculations. Actually, the hard part is about finding that this is small and this is small. Okay, let's jump to this problem. This problem is quite standard. You should know how to solve it. You have to answer some offline queries about how many pairs you can make in an interval. Okay, actually, you have some people with some different colors. You are given some L and R, and you have to determine how many pairs of distinct people with the same color you can make. Yeah, also disjoint pairs. You have, for example, this subarray, and you can pair everyone 2 with 2, 3 with 3, and 1 with 1. If you pick this subarray, you can only make 3 pairs anyway, because okay, for a fixed color, if we have k occurrences, we can make floor of k divided by 2 pairs. And yeah, so the query just asks you to find sum of occurrences divided by 2. Okay, alternatively, you can just say, okay, I can make pairs with all the people except the ones which, okay, if you have some color, if it appears an odd number of times, there's an element you cannot pair. So alternatively, you can just count the number of people, the number of colors which appear an odd number of times, right? Here, 3 colors appear an odd number of times. So you can actually pair 9 minus 3 people and make 3 pairs. Yeah, and how to do all that fast. Okay, first of all, let's notice that segment 3 here does not work well. Because how to deal with multiple colors simultaneously with segment 3? Yeah, so we should try an entirely different approach. Okay, do you know about Mohs algorithm?
I've heard about it, yes.
Okay, actually, the point of Mohs algorithm is that you add a square root of n factor, but now instead of answering arbitrary queries, you just need to be able to move L and R one position to the left or to the right. Okay, let's do an example. Let's just plot all the queries. We have L and R. Okay, so we expect L to be smaller than R, so the queries are here. Okay, but that's not so important. And here are a lot of queries. And okay, what one would normally do is answering this, then answering this, etc. But okay, maybe sorting by L, sorting by R first, and then answering. Okay, in this case, let's assume we can move from R to LR plus minus 1, or even to L plus minus 1 R. Okay, what does this mean here? Here it means that okay, we are doing a step on the plane, and with multiple steps we can reach another query, answer, and continue like that. Okay, for example, if we visit points in order of L, do you think it's fast enough?
It might be fast enough.
Yeah, okay, but actually,
Because,
yeah,
what were you saying, sir?
yeah, okay, the problem with that is that, okay, first of all, we can make cases where it's definitely not fast enough. Okay, let's let's draw this again. And now let's suppose we have to answer these queries and go up and down. So we need OFAN steps here. Then we need another OFAN, etc. So in total it's OFAN squared. Okay, even if the points are random. Okay, just to clarify, let's go back to the interpretation with the array. You have this array with several elements. And what are we doing? Okay, let's say we have to answer queries 1, 1, 2, 12, 3, 3, 4, 12. Okay, we are saying let's start with answering in this interval. Then let's just move like this. So you need of n steps to jump from this query to this. And yeah, that's too slow. Even if, okay, let's suppose we have all the left endpoints. Even if the right endpoints are random, the average distance between two consecutive values of r is like 1/3. So the average complexity is n squared anyway. Okay, so what we should try to do is just changing the order of the queries we answer. Let's remember that the queries are offline, so we can answer in any order. Okay, in this specific case, okay, we can just choose this order, for example. And yeah, that becomes often. But in general, that's not possible. In general, the queries might be much messier, and but still we can find something fast enough. We can find of n square root of n. And okay, the point is, okay, let's draw this again. And divide it into blocks. Okay. What we were doing earlier was sorting by L and doing these. Okay. what we can actually do is sorting by block. Okay, and what happens in every block? You move right only length of block times at most. Okay, let's call that S. Okay, so these steps have length at most S. Okay, what about the vertical steps? So this is of n times S. You have n queries. Okay, we should say Q. Actually, let's assume n equals Q. What about the vertical steps? We're doing something like this. Okay, the important part is we sort by block, but okay, the blocks are very tall. So it's not so important to visit points in order of L, in order of this coordinate. But okay, now it's more efficient to visit them inside every single block in order of R. Okay, in such a way that the green, okay, the total length of the green arrows is at most of n in each block. Okay, of course you have to repeat in every block. How many blocks we have? So this is n. The number of blocks is n divided by s. And inside each block, you move O of n vertically. So you have O of n times n divided by s. Okay, so the complexity, the total complexity of is O of n s plus n squared over s. And we should try to find a good value of s. And yeah, for example, usually we use n s equals
S could be square root of n.
Yeah. So this is O of n square root of n plus n square root of n. Okay, how to calculate that? Do you know derivatives?
Of course, so we know derivatives.
Yeah, okay, so you can just do this ns plus n squared over s equals 0. And so in this way we hope to find a minimum of this function, so a value of s such that this function is small. And yeah, the derivative should be easy to calculate, and it's n plus
minus 1 over
n squared over, okay, I'm new at derivatives, sorry. Can I calculate a derivative? I don't know. Just this equals 0. Yeah, so we have ns squared minus n squared equals 0. S equals square root of n. Okay, that's it. Yeah. So here, indeed, can we use Mohs algorithm? Can we move from LR to LR plus 1, RR minus 1 fast? It means we are trying to add or remove a person. And what we are trying to count is the number of elements which appear an odd number of times. So, okay, the only color that's affected here is the one we add or we remove, and we have to check if it appears an odd number of times. And yeah, this is possible. You can just store some prefix sums. I mean some vectors which contain all elements of some color. Okay, and in this way you can determine in how many elements of some color there are in a range, but it's not necessary. You can calculate everything on the fly. When you visit an interval, you want to store some useful information. For each color, how many times it appears, and of course the answer. In this way, you can just add an element. You had already saved here how many times it appeared, and it's just about updating a single element. Here it appeared one time, and okay, here you add it, and it appears twice, and so the answer is increased by 1. Okay, maybe we'll try to implement it later if we have time, but I think we will not have enough time. Okay, let's see. Let's see the two other problems first. Okay, anyway, was it clear? Do I need to explain Mohs algorithm again? Well, it's a very useful way to answer queries, especially the hard ones where you cannot really use a segment tree or something. Okay, so let's jump to this new problem. Here we have a tree, and okay, again, each node has some color, and we want to determine the sum of 3 distances, where, okay, the distance is the number of edges over a path, over the path between I and j, and okay, but now we want to calculate this sum only over pairs of nodes with the same color. So we have these 3. 1, 2, 3. Okay, let's say we color these nodes red, these nodes green, and these nodes blue. And now, okay, we want to find distance between 1 and 4 plus these plus these plus these ones plus this, right? Okay. So first of all, let's try to solve some special cases. Okay, of course, if you cannot solve the special cases, you cannot solve the whole problem. But if you can solve the special cases, maybe they are useful also to solve the whole problem. Okay, for example, what are some special cases in this problem? How can we set colors? Okay, it's a question I'm asking to you.
Yes, sir. I think the nodes is the same with the same number and have the same color.
Yeah, okay. If all the n nodes have the same color, can you solve the problem?
I'm not sure, sir.
Okay, there are multiple ways to solve this, and you should know this problem. I mean, it's standard. You need it as a subproblem so many times. So let's just solve it. Okay, let's draw the same tree as before. And let's assume every node has the same color. Yeah. Okay, I think the cleanest way is, okay, let's count, let's do a double counting. For each edge, we want to know how many paths contain it. For example, let's choose the edge 2, 5, okay? And you want to know how many paths contain the edge 2, 5. And yeah, you can get that they are the ones which start somehow here and end here. Okay, if you choose one node from okay, let's use two different colors. If we choose one node from the blue component and one node from the green component, every path that passes through these two components should pass through the red edge, right? Okay, got it. Yeah, and now how to solve the problem? Yeah, with every node with the same color in linear time. Okay, again, I'm asking to you.
I'm having internet issues, so I'm sorry.
Oh, no worries.
The stream keeps disconnecting.
Okay, maybe it might be.
And also, sir, I think everyone's silent because they haven't studied trees yet, including me. I have studied graphs a bit, but I'm not very good at them.
Okay. Actually, I knew there was this risk while preparing square root stuff. I mean, usually square root problems are not so easy and also require something else. Okay. So anyway, okay. So you know DFS, right?
Yeah, depth first search. Yeah.
Yeah. Okay. And now, okay. Let's just run DFS over these three. Okay. Let's start from node 1. And yeah, whenever we visit a node, okay, now let's try to do some DP on these three. Where actually, okay, first of all, what's our goal? We fix the red edge, and we want to know how many nodes we have here and how many nodes we have here. So we want to find the size of the subtrees. You have some node and you want to know how many nodes are his descendants. Okay, let's root the node the tree on node 1. Do you know what it means to root a tree somewhere?
No.
Okay. Okay. In general, you're given the tree as a list of edges, and what you can do is, okay, you decide. Okay, node 1 is the most important one. It's the root, and then okay, these nodes have depth 1, depth 2, depth 3, etc. And For each node, there are some descendants, which are the nodes just under him, and some ancestors.
Yeah.
Okay, so the descendants of node 1 are all the nodes, and the descendants of the leaves are just the leaf itself. And yeah, actually, for each node, it's enough. Okay, you want to calculate the number of descendants, and you just do dp on 3, which is okay. When you are in a leaf, you stop, and the size is 1. Otherwise, the answer, the number of nodes in the subtree, is 1 plus the sizes of the children. Okay, if you have node 5 here, the size of the subtree of node 5 is 1 plus this size plus this size. Okay, so actually it's not hard to calculate. This is 2, 1, 2 plus 1 plus 1, 4, 1 plus 4 plus 1, 6, 1 plus 1, 2, 6 plus 2 plus 1, 9, and in fact the size of node 1 is n. Okay, does it make sense?
Yeah, of course.
Okay, and now for each edge, okay, you can consider each edge as a vertical one, which goes from an ancestor to a descendant. And okay, so here we don't know yet how many nodes we have here, but we know how many nodes we have here. So for each edge, we just choose the lowest node, and here we know that there are 4 elements in the subtree. So here there are n minus 4 nodes. So I just here we have 4 times n minus 4 paths, and yeah, actually we can calculate the same for all edges. We have here 4 times n minus 4, 1 times n minus 1, 6 times n minus 6, etc. Okay, and sum all these results, and it's linear.
Okay, so we just do pre-computation. We compute the size of all subtrees, and then we deal with this formula, right?
Yeah, but
we sum all of these formulas.
This is of course for a single color. Okay.
Yeah, of course.
Now, but okay, what if there are several colors? For example, okay, let's try to find a solution even if it's slow. If we have 2 elements of each color, you have 2 red nodes, 2 green nodes, 2 blue nodes, how to deal with that? Okay, I guess I have to...
Doing each one individually would be slow, right?
Of course, if you do that with this algorithm in linear time, yeah, it's slow. But if a color appears only twice, you just have to calculate the distance between those 2 nodes. Okay. Do you know how to calculate the distance between 2 nodes fast?
No.
Okay, sorry if I'm spoiling the 3 lecture, but okay.
No, of course, sir, feel free.
I mean, I did not expect that because I just didn't know you hadn't done trees yet. But okay, trees I guess are more important than square root stuff. So even if you repeat it twice, then no worries. Okay. So let's do the usual DFS, and okay, with that DFS for each node you can also calculate the distance from node 1. Okay, actually you can do that also for a generic graph with BFS, but here even the DFS works because you only have one path between every pair of nodes, so you cannot calculate a distance which is larger than the actual distance. Okay, so we divide the tree into layers with increasing distance. Okay, and now if we want to calculate distance between node 4 and node 8, it's almost the sum of depth, the sum of the depth of node 4 and of node 8. But okay, let's draw the path. It's this one. Yeah, and we can divide it into two parts. Okay, you can see that the path goes upper, and then it reaches some node, which is called the lowest common ancestor of nodes 4 and 8. And then you go down again. And yeah, the length of the path is the length of this part, which is okay. Let's call it. Okay, this is the depth. Let's call it d. We have d of 4 minus d of 2 plus d of 8 minus d of 2. In general, we have distance of E plus distance of J. Okay, this is the depth. Distance between I and J is depth of I plus depth of J minus 2 times depth of lowest common ancestor of I and J. Okay, the only remaining part is how to calculate the lowest common ancestor, but okay, trust that you can calculate it in a constant time of 1. Okay. So for each node, for each pair of nodes, here we have n divided by 2 pairs, and for each one we can calculate the distance in O of 1. So again, we spend O of n. Okay, does it make sense? Someone sooner or later will explain you how to calculate lowest common ancestor. But
yeah, sir, just carry on, because I guess we can't get the whole thing because we haven't studied trees, but we're following somewhat.
Okay, the next problem is not about trees, so that's fine. Okay, anyway, now you don't really need some other tree algorithm to finish the problem. Okay, so we've solved the problem in 2 special cases, which are all nodes have equal color and the same color, and we have pairs of nodes with the same color. Now we want something in between to solve the general case where we can have 3, 4, etc. Nodes with the same color. And yeah, so actually we can try all pairs. For each segment I've drawn, you can calculate the distance in O of 1 and add it to the answer, and that's it. But yeah, of course this is too slow in when each node has the same color. Otherwise, you can just use the O of n algorithm for each color, but that's too slow if you have many colors. In this case, okay, we notice that we have 2 algorithms which perform better in some situation and worse in some other situation, and we should try to mix them up. And in this case, it's very easy. So we have algorithm 1 for a single color. We span linear time. Okay, here we have to modify a bit because we shouldn't calculate the size of the entire subtree, but just the number of nodes of some color. But it's almost the same. Here we were summing 1 plus sizes of subtrees, but here, okay, the 1 appears only if the node has the correct color. By the way, otherwise we have algorithm 2. Again for a single color, which requires O of k squared, where k is equal to the number of occurrences. Okay, but what if for each color we just choose the fastest algorithm? If the color appears 3 times and then is equal to 10 to the 5th, we use this algorithm. If the color appears 10 to the 4th times, we use this. So we actually span a minimum of n k squared. Do you think this is fast enough?
Can you show the constraints, sir?
Yeah. Okay, let's try to plot something. Okay, ideally, we would have an OK algorithm like this. Okay, if we span O of k, it's O of n in total, right? Because the sum of k is n. But here we have something kinda slower, right? Okay, first we have k squared, right? K squared goes like this. Okay. But then we have an upper bound which is n. Okay, so instead of the yellow complexity, we have the white complexity. And when is the white algorithm? I mean, just find the fastest algorithm between these two. Much slower than the yellow one, which does not exist, and it's O of k. Okay, you can see that the worst point is this one. Okay, this is the point where the ratio of the two algorithms is maximum, where the slowdown is maximum. Okay, actually we have a slowdown of minimum between n and k squared over k, okay, which is minimum between n over k and k. And yeah, with some calculations, you can find out that the worst point is this one. Okay, so the slowdown factor is at most square root of n. So the complexity is actually O of n times the slowdown, which is O of n squared 10 in total. Okay, otherwise you could just say, okay, let's divide it into two parts, nodes which appear, colors which appear at least square root of n times, but there are at most square root of n of them. So we spend O of n times square root of n, and not here. And there are colors here. There are at most n colors, and we spend square root of n for each color. No, actually, we can spend up to n. But yeah, also here the complexity is at most n square root of n. So you sum them up, and it's n square root of n anyway. Okay. Did you get the slowdown idea? Which is, okay, here the ratio between the linear algorithm and our algorithm is not so much, it's square root of n at most. So yeah, we can get accepted. Actually, there are some n log n solutions, at least 3 of them. But okay, first it's better if you learn some standard algorithm on trees, and then you can try to find these solutions. But yeah, n square root of n is usually the easiest to write here. You don't need any particular. I mean, the hardest part is calculating lowest common ancestor, but you should know that. I mean, you should learn that very early, very soon. Okay, do we still have time to solve this, or should I leave it as homework? Actually,
You have to, so.
You have time. Okay. Let's go fast. Actually, my plan was to stay here 1 hour and leave some problems as homework and then discuss them next week. But yeah, we can discuss this first. So yeah, you have a game, which is you have an hidden array. Okay, this problem is interactive. You have an hidden array, and the computer asks you to find the kth 0. Okay, but he asks you several times. And in the meanwhile, you can ask sums in some subarrays. And every time you guess the kth 0, it becomes a 1. And the computer can change the value of k. So, for example, the computer asks you to find the 5th 0 from the left. You find it, it becomes a 1. Then you have to find the second 0. You find it, it becomes 1, etc. How to find it? You can ask the sum from L to R, but you cannot ask it too many times. The array has length 2 times 10 to the 5th, and you receive 10 to the 4th questions, and you can ask 6 times 10 to the 4th questions. Okay, so first of all, let's try to create some subtasks. Okay, actually there is a subtask in the actual problem, but okay. Can you guess a subtask here? Let's try to find some, to solve some easier version. For example, t equals 1. You just have to find the kth 0 once. Okay, how to do that? Okay, I'm asking you. Okay, first of all, is the statement clear? Yeah. I mean, of course, with a linear search, that's not possible because you have too many elements. Let's try to binary search. How to binary search here? You need a way to determine how many zeros you have in a prefix, okay? if the prefix contains more than k zeros, you go left, otherwise you go right, and that's it. Okay, how to count the number of zeros in a query? Oh, okay, maybe I didn't mention the array is binary.
We do a binary search from 0 to k.
Okay, and what you ask in the meanwhile?
Okay, I just read the problem. I didn't see what the query said. It says find out the sum of all elements in positions from L to R.
Mm-hmm.
It answers that, right? It gives you that.
Yeah.
Well, since it's binary, the number of zeros is just the length from L to R minus this sum that it gives you.
Yeah, so now do you agree you can binary search?
Yeah, but not standard form of binary search, I guess.
Okay, so let's create an array here. And we have to find the fifth.
Okay, I think I have an idea.
Mm-hmm.
We search first. We search from 0 to k. We find the number of zeros. If it's equal to k, that's our answer. If it's smaller than k, we split the array into two and search. If it's more than k, we split again. If it's less than k, we search. I'm not sure what to do in that case.
Okay, but yeah, you said okay. The number of zeros is the sum plus the number the length minus the number of ones, which is the sum. Okay, but yeah. So in a query, you can find the number of zeros from L to R, right? Okay, let's make things simpler. Okay, now we are finding the number of zeros from 1 to R. So, okay, let's just draw it. A number of zeros from 1 to R. Okay, but okay, of course the number of zeros is increasing. You have 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, 5, 5, 5, 5. Okay, so this is an increasing array, and you have to find the first element which equals k, right?
Yeah, of course.
And that's it. So you ask in the middle, the answer is greater than or equal to k, so you should go to the left and ask this, but this is too small, so you ask this is still too small, and okay, this is the answer. Okay, how much time does it require? Okay, actually we reduced it to a standard binary search. We are just searching a value in an increasing array.
Yeah, and we can speed it up just a bit by looking from 0 to k instead of the whole array all the time. Because it can be more than kz. It can be more than k zeros from 0 to k, right? Or from 1 to k.
Right. Yeah. Okay, in any case, we spend log n. With your idea, we skip the first k elements because, okay, the sum. Okay, we cannot have too many zeros in the first k positions, so it's instead of log n, we have log n minus k. Yeah, but actually, even if k is around n, around n over 2, we have log, okay, it's log 2 actually. Log 2 of n over 2, which is actually log n minus 1. So we just save a single query on average, which is still not enough to solve the full problem. You have t questions, and this would require t log n. So more than 10 to the fifth questions. Okay, but yeah, we should use the fact that the array does not change too much between queries. Okay, for example, if you know all the array in advance, how many other questions do you need?
What? I don't understand.
Okay, okay, let's suppose the array is not hidden, right?
Yeah.
Okay, if the array is not hidden and you have to play the game for t rounds.
Yeah.
Okay, how many other questions do you need to ask?
You don't need to ask anything, really.
Yeah, because you know the exact array at any moment. So
Yeah.
that's it. Okay, yeah, but okay, we can actually simulate something similar by just asking all the elements at the beginning, but of course it's too slow. I mean, it's we are asking too many questions at the beginning. 2 times 10 to the 5th. Yeah, but can we do something in the middle? I mean, ask some partial information about the array so that we can speed the search up during the T rounds.
Maybe ask for the number of zeros in the entire array.
Okay, if the number of zeros is, let's say, 2k, I think it's not helping so much. Yeah, but of course this is a single query, so okay, let's do it just in case. It cannot hurt. Okay, but somehow we need more information. We need to speed the search up a lot. I mean, not a lot as in asking all the elements, but almost.
Maybe we can use a factor of square root of n somehow. Ask for each chunk, each square root of n chunk of the array, what the number of zeros in there is, perhaps.
Yeah, okay, that can work. And let's actually try to decide the correct size of the blocks. Okay, you have an array, you divide it into blocks, like this. Okay, and after that, how much time do you, let's say the block have size s. Yeah, so the initial queries are n divided by s plus, okay, how much time do we spend to answer a single round, a single question by the computer?
What do you mean?
Okay, now that you know the sum in all the blocks, can you speed the binary search up?
Yeah, somewhat. You get rid of the first few blocks, perhaps, like from L to R, and focus on the last block only.
Let's do a concrete example. Okay, we have, for example, k equals 5. Okay, and now you know that here you have 2 zeros. Here you have 1 0. Here you have 7 zeros. And here you have 3 zeros. Okay?
So you go through each block from L to R. If that block has the kth zero, we search in it. Do you get what I'm saying?
Yeah. So, okay, we can actually store the prefix sums of number of zeros. We have 2 zeros until now, 3 zeros, 10, and 13. Okay, and of course, it doesn't make sense to search here since there are at most 3 zeros. It doesn't make sense to to search here because here we already have 10 zeros. It's like some queries are already answered. You know that.
So we search.
Yeah, you just search here.
Yeah.
Okay. And yeah, so how much time does it require? What's the length of this block? S.
Square root of n or s.
Not necessarily. Let's find the correct value of s. Okay, it's always square root of n. Anyway, it's now we know we spend log s for a single query, so t times log s. Okay, and now we want to find the optimal value. Okay, actually there's a ceiling here, but okay, for now let's find the optimal value without the ceiling. And okay, again we have n divided by s squared plus t divided by s, right, equals no, it cannot be right. Yeah, there's a minus here. Equals 0. So we have t times s minus n equals 0. S equals n divided by t. Okay, n times n to the 5th, t 10 to the 4th, so it's around 20. Okay, in practice you have the ceiling here. So you can choose s equals 32. Does it work? Let's try. We have divided by 32 plus 10 to the 4th times log s, which is 5. Yeah, it works. Okay, it's not even close to square root of n. Here we need a much smaller value.
By the way, Mr. Stancanelli, are you recording?
Yeah.
Okay, nice.
Yeah. Okay, I think that's it for now. Oh, I even got wrong answer on this problem. Okay, I've never fixed it. I don't even know if this solution should be correct or not. But yeah, the solution I've told you is correct. Trust. Okay, that's it. So in the document, actually, there are some additional problems. these ones. Unfortunately, here there's a 3. Okay, so you'll solve it after dealing with trees. Okay, in the other problems there are no trees, so don't worry. Here there's a graph, and okay, here. Okay, it doesn't seem like you need to use square root, but okay, you'll see. Okay, that's it. Okay, most probably we'll discuss solutions next Friday. Okay, in the meanwhile, feel free to implement the 4 problems we've discussed today. And here there are sketches of solutions in the document I've sent. Okay, so that's it. See you.
Thank you, sir. We appreciate it.
Nice.